Hello? Ah, still off air. Okay, I'm trying to close this one and see if I can open it. Hmm. All right, it says I'm live now. Okay. Okay, we've gone live for teaching mathematics through problem solving. I'm just going to try and share the link. So I think we are live now. I'm just going to check what I see. Okay, so we actually are live now. We're supposed to be teaching mathematics through problem solving. Let me just drop this one in the Twitter. Okay. All right, we are here. Because I messed up the YouTube streaming so badly, it looks like, yay, we made it. I'm not in Hangouts, and I'm not sure if I can drop my slides in here, which is just what I'm looking for. So we learn from doing with all these technology things, and yeah, it's a learning experience. I think I totally messed up the encoding, and that's definitely what happened. So what I'm going to do is drop the links to the slides in the chat box, which is excellent because you can have them. So I'm going to get the shareable link, and I'm going to refer to them. So those were slides for today, and so if you want to just follow along, I can just talk you through some of them, which they won't be on the screen in the presentation, but the evidence will be in the actual link, which anyone can take and make a copy of. And that's almost as good, not quite as good. And I guarantee that I won't botch the streaming next time. The good news about the slides is there's a table about teaching through problem solving that has my axioms that are actually in the book I wrote on this topic, which is coming this fall through Rowman and Littlefield Press, which is very, very exciting. Let's put the slides right beside so I can refer to both. So you have to look at me, but then you can get the tab beside and you can look at the slides, and we can refer to them by number. And life is how it is, so we carry on. Sometimes your YouTube encoder fails, and sometimes it doesn't. So the first slide was just about math is play. And that's just something I like to say and talk about and think. For those who were maybe following along with NCTM in Washington last week, the exit keynote was delivered by Francis Su, a talk called Mathematics for Human Flourishing, which I highly recommend you watch. But he talks about play being a most basic of human desires. And I put one of the chapters in the book about that. But as you can see on slide 4, I just left the link to the TED Talk. And I had a really interesting talk about that. A colleague had watched it, and he was sort of saying, well, what sort of TED Talk is this? Is this an evidence-based one? And I was saying, well, actually, I'm just really saying that mathematics can and should be more playful. And so it's more of just like a way of being and less so than even some kind of formal pedagogy. So what I was intending in that TED Talk was just to present this idea that mathematics could be more playful, because if you ever do a TED Talk, you just start from the idea. And I illustrated it with some examples. And so that one would distinguish it from one that was maybe heavily evidence or science-based. About me, well, everyone here knows that. Slide number 5 is just something that I like to show sometimes. And so we as humans are best at thinking. I always say that. And then computers are best at computing. So I tweeted this the other day. I said, compute this. So some long string of numbers that goes to 0 at the end. And I took it from one of Martin Gardner's books. And so he was known for Scientific American columns and recreational mathematics. And he had like many, perhaps thousands of them. And this was just one of them. And you know, if you don't notice that there's 0 at the end, or if you don't think about what that means, then you might just start calculating. Actually, I think a computer wouldn't have a choice. It would probably have to go in order. I don't think computers multiply like we do. They use a different process, I've heard. But now imagine this. Imagine you have some rectangle, because we can define multiplying as a rectangle of a certain length times a certain width. So we have a whole gigantic string of numbers. Let's call that the length of this rectangle. But lo and behold, the width is 0. So there is no area to speak of if you think of it that way. I use this one in presentations. Typically, teachers will get it right away. So imagine there's some brackets around all the numbers, except for the 0. Makes it easier to see. But we're best at thinking. Now I'm going to attempt to bring in the Matthews notepad so we can try a couple problems. And I've had some good success with recent webinars with teachers sharing work through Matthews. If the evidence, if we can somehow get them in this chat box. Actually, our best option this morning is I'm going to make this Google slide deck can edit. And so what we'll do is for doing the work in Matthews Notepad, we can just take a screen capture, or you can save it as a JPEG, and we'll put them right in this presentation. So the evidence, for anyone to find this MadPD useful in the recording, they will see and hear me talking, and they'll have the link to the slides. But I think it's best if our work goes in the slides. Okay, so I think first I would talk about skipping ahead to number 7 in Google Slides, which says, give me a problem and not an answer. So answer getting, we know this, is one of the functions of kindergarten to grade 12 math. We know this. Chug through, get the answer some way. So, but I might say, this homework said, think of a math problem. So a lot of mathematicians, their work is more thinking of problems and thinking of new questions as much as it is getting to an answer. And we know the answer getting function has traditionally been strong. That's never going to go fully away, nor should it, because getting answers is powerful. But I think it's the teaching through problem-solving mentality. Kids can come up with problems. Problems generate more problems. I'm going to jump to number 9, because that actually is the first table in the book that I wrote, which is codenamed Teaching Mathematics Through Problem Solving in K-12 Classrooms. It doesn't have, and may not have, a snappy title, but it is exactly what it sounds like. Trust me on that. So I'm going to go through these because I wrote them, I believe in them. So an axiom in mathematics is something that we proceed from. And I think that in K-12 classrooms, we always have all kinds of things that we've internalized proceed from, we take for granted. A mathematician wouldn't necessarily do that. There was an interesting and perhaps strange group of people called the Bourbaki group in France, like 1930s to 1970s or even later. That's because it wasn't one person. They were a bunch of mathematicians, and they were trying to build mathematics from the ground up, so without any axioms. So if nothing is axiomatic, as it were, you have to prove everything. So the Bourbaki project started by proving that 1 + 1 = 2, which was great. It could be the basis of all arithmetics. It's basically the counting principle. But it took them about 100 pages to do that because they didn't take it for granted. So if you think of this, we have all these compressed axiomatic things that we believe in and we don't necessarily state. That's what axioms are. For the purpose of the book, though, I wanted to address them sort of chapter by chapter and with examples and so on, what I believe. So axioms, so proceeding from the idea that there exists a school of mathematics that's inspiring, interesting, playful, and elegant, where students work on challenging problems together and alone and share their thoughts, ideas, conjectures, and reasoning. And this was sort of the mission statement. I said, there exists is also a symbol in mathematics. It's a backwards E. So it's sort of bringing something or stating something, bringing it into being. And so this was my mission statement. It was basically the coda for this book. Number 2, problems are tasks or questions which are interesting and contain big mathematical ideas. And so I thought, well, you know, and it's in this slideshow, is 49 times 21 that I used with in a webinar this week, but it can be just a calculation or it can be something interesting to think about in its own right. And I think that's just one little example. We're used to that, well, the problems and tasks have to be open and they have to be, you know, sort of the biggest possible things, and they don't really need to. Real world context can be misleading as well, but they do need to contain big mathematical ideas. Okay, and interesting problems are the mainstay of instruction in mathematics classroom. Problem solving is not a reward, special event, or once in a while thing. Very interesting with classrooms that I have had is that there's these old binders where in around the late 80s, early 90s, we thought it was best to teach about problem solving strategies. For example, you may work backwards. You know, usually you work backwards through a series of operations to get to a number. So the idea was that you could explicitly teach that strategy. And that kind of failed. It was sort of like, okay, well, it's Friday, time for a problem, kids. It's sort of like, you know, you've eaten your broccoli all week, here's a cookie kind of thing. But meanwhile, the Ontario curriculum at least states that interesting problems are the mainstay of instruction. And it must be so. It says so. It says so. All students can be taught to think mathematically. So this whole process of breaking things down to their essentials, stripping problems down to find out what's there, and then having, I guess, a line of attack on problems, but also thinking logically. This is sort of a massive thing to think about, because thinking mathematically is, well, it's a slippery thing to define. When are we thinking mathematically? I would suggest more often than you think, but it's tied up into thinking like a mathematician. And we can build those habits of minds with kids and help them to think mathematically. That one is, yeah, and it has to do with recognizing the structure of problems and having tools and strategies to use. Problem solving is an iterative, ongoing process of thought. You know, and again, I think what we get kids to think about is us showing that we value just thinking in general, and that thinking is ongoing, and that we can be quite good at it. But I thought the iterative part, that maybe just because this class period is over, this problem doesn't need to end. That's part of this mean-ended thing that we have with kids. And it just doesn't really have to be that way. So I've had kids, when I've had recently had a classroom, most recently rather, a few years ago, and that kids would think of a problem overnight and just carry on the next day, because why not? That's one example. Number 6, I thought, is massive. So representation I came across this great paper which talks about sort of the mental action, so the verb part, and then representing it on paper or even with manipulative, sort of the thing itself. So I've produced this array to show 8 times 3, or whatever you've produced, right? I've produced this number line. I've used this number line. And so, but it's that bringing into being, and so I do a lot with grade 7 and 8s now, and a lot of times they don't have the mental process for bringing into being. Okay, and since Heidi's here as well, and you've done a lot of work on visualizing, I'm always thinking, well, what do we think about when we think about a problem? If we were to even close our eyes, can we, so as Heidi says, draw on air, but can we also represent it in our minds? Can we begin to, and then bring it into the world? So I think there's something missing there sometimes in instruction. In representation sometimes is just us reaching for the tools. Like, you know, this 10 frame, these pattern blocks, these Cuisenaire rods can represent something. But it's also going back and forth between different representations and seeing how they have the same mathematics in them. And a really great example is always algebra. So a graph has the same information as that function, like the equation that that you can use for it. But it could also be some kind of picture pattern, like the growing patterns we're used to. Number 7, basic skills and problem solving are not at odds, but mutually complementary. I had thought that it's time for us all to drop this whole, well, procedures must come first always, or concepts must come first always. I think in almost every case the concepts should come first, but I think it's recognizing that there's this interplay, and so that was one of the papers that inspired me the most, was talking about how one informs the other and back and forth. And so we should stop thinking of it as like this on switch, off switch, or this either or thing, and looking at how these things develop together. One really nice example is a bit sadly, it's the era of Kumon and Spirit of Math and all those places. But so you could teach a grade 3 and you could be trying to go through multiplying, but a kid would just be like, oh, I know this standard algorithm. And I've seen teachers that sometimes want to take that away from them. And in the meantime, that's what they know. That's a tool that they have. So I think it's sort of like, know the procedure first. Hey, back up. What actually is multiplying? Learn the concept first. What actually is multiplying? Build up to the procedure. Just recognizing that both are going to work just okay. It just depends on how we run our classroom. And full instructional guidance is necessary. There's a huge difference between that, letting kids work for half an hour, letting them hit the sweet spot, versus letting them flounder. And I think the slight misnomer is that we can just step back too much and not have to instruct. It's just when we instruct. And I fully believe we can give a problem, instruct in the middle, instruct along the way, also instruct at the end. I fully believe that. But it's just not leaving the puzzlement at the end. And mathematics classrooms are places of talking, thinking, conjecturing, and wondering about the mystery and beauty of mathematics. Of course. And mathematics can and should be full of curiosity, creativity, and play. So I wanted to include that because I did write 40,000 words on it, so I spent a lot of time thinking about it. Depending who's in the room, there's a couple problems I've been using a lot. So what I'd like, and I'm just going to stay on to see this, but mathies.ca notepad tool. Okay, and let me drop the link in. I'm a huge believer in mathies.ca notepad tool, and I had an awesome OTF webinar this week. Only 4 people came, and that's because it was up against the Raptors, and also it was Joe Bowler live at OAME. But 4 people came, and they did great work. And I've used Mathies Notepad in previous webinars. Okay, so this is Mathies Notepad tool. The developers have been consistently making this better. So what I want to try, and the evidence will be in the Google Slides that you'll have to take away. So either number 8, the mutilated chessboard, which is either Martin Gardner. So what you would do you would screen capture, save, go to Matthew's notepad, open that, draw on top of it, save your work, put it in the Google Slides. Or number 10, sum all integers from 1 to 100. I go back to the well for this one a lot because it's awesome and adaptable to basically K to 12. And it has to do with, so listen, a young Carl Friedrich Gauss realized something about this, and a lot of adults and kids alike will realize it. So your option for number 10, if you look at number 11, actually there's 100 square. You could screen capture the 100 square, pull that into Matthew's notepad, draw all over it. Okay, and tell me the sum of all integers from number 1 to 100. So 8, 10, and 11. Also, if you like, because these are supposed to be shorter and I could go with this all day, number 16 was what I used the other night for OTF, 49 times 21. Participants did awesome stuff. So all you need to do for that is open the Matthew's notepad and do something. Like just do something that shows me something about 49 times 21. I'm going to assume something that's not the standard algorithm because we all know how to do that. If you look at slide 17, there's just sample of the work using partial products in the area model. Okay, there's a few bonus problems later. So I am going to model good practice. I think I'm going to tackle summing all integers from 1 to 100. And I think I'm going to screen capture the 100 square and do the work live. So, and I see 4 people there, and so I'll know that, yeah, I mean, if you're still engaged, we'll drop our slides in. So I'm going to take, put my money where my mouth is and show you how I would use Matthew's notebook tool. I promise that if I do this again, I will have the proper screen share. As I said, I thought I was ready this time and I was blindsided by YouTube problems. And I'm going to describe it in words. I'm opening Matthew's notepad. You'll see that you can write on a blank screen, or you can write on a grid. There's a bunch of tools. There's a number line. And I'm going to leave open one more thing if you are, that you could use the chat box here to drop in some ideas. I may recommend that if you have not seen it, that the mutilated chessboard pushes you to do some interesting mathematical thinking. That's how I know it's just one of these technological days. I've used Matthew's notebook like 800 times, and now it's not loading. I blame it on Friday's storm. Somebody's shingles blew off on my street. Somebody's front door mat is right outside my house as well. And of course it's not loading. So what I'm going to do while you're working, so there's not too much dead air on the recording, I'll just talk about a couple more of my slides. And if some of the mathy stuff comes in, so be it. That's great. We'll have it. If not, you'll know my sort of thinking here. I think that our students can very effectively use Matthew's Notepad. It's turned into a terrific, terrific tool. Okay, so I'm just going to cover a couple more slides in the time we have. I'm not sure what time we'll sign off. It's supposed to be half an hour. And let me talk through the slides so you have them and you know what they kind of mean going away, or what I think they mean. Number 6, how many squares are here? So I just took a photo of my chessboard that I've had since I was a kid, and I said, okay, sure, if this is the task, I can pose it in 5 words. And sure enough, that's sort of a classic problem for a task. Now, if it was grade 7, I might be looking at squaring, like an 8x8 square, also contains 4x4s, 2x2s, 1x1s. That's where I was going with it. But if it was grade 2 to 3, and we might be looking at arrays and multiplication facts, I might be doing something with just 8 times 8. I might just pull back and say, not worry about all the little squares. Okay, so I think in teaching through problem solving, we have versatile tasks that can go across grade, but you know what's key? Know thy curriculum, like basically above all else. So if I have a picture of a chessboard, again, so let's exclude grade 1. It could be about adding. So let's talk grade 2, multiplication, the very beginning, skip counting, grouping. Grade 3, definitely multiplication facts. Okay, jump ahead to grade 7, exponents. I might do something with that. Do know the curriculum and attach any task that you use to the curriculum. Play builds hope, as that was number 12. I 100%, and I see the YouTube to the original talk is there. There is since maybe a more slick NCTM Washington version. I mean, look, he's a professor at Harvey Mudd College. He just brings the house down. It's amazing. He talks of an inmate actually who teaches himself mathematics to become free. It's extremely inspiring rather. Take 55 minutes and watch it, or track down the newer version. Mitchell Resnick's book, Play is Just for Kindergarten, Let's Hope Not. So I'm strongly connecting sort of a spirit of playfulness to a spirit of teaching through problem solving. I don't see how those two could not be linked. Slide 14 is just a couple points from Mr. Resnick's book if you haven't read it. And I guess it just goes to show, like, yeah, play versus playfulness. So kindergarten curriculum, you know, kind of mandated curricular play versus just being playful, approaching mathematics playfully. Number 15 talks about like, what would this pedagogy of playful mathematics look like? And what would it feel like to everyone in the room to learn through interesting tasks and to be playful? For 16 and 17 there was a broader point, and I've kind of made it. It was just sort of how Keith Devlin put it nicely this week in a blog post, that arithmetic used to be like the barrier, or as he put it, the cost to entry to do mathematics. And we have machines to do a lot of it. And so, like, depending on where I was and how much time I had, I'd just plug 49 times 21 into my calculator. But like, it's really interesting to try and multiply 2-digit by 2-digit in my mind, I find. And I've done it live, you know, numbers almost this big with parents and kids alike. And they can do it. Number 18 had to do with Tenzi, which is really common in chapters and other places. It's like $15, but I think it shows how, like, if you were to take that tube of 40 dice, you could attack some really big ideas about probability. And so teaching through problem solving for probability a lot of times is experiencing it, right? Number 19 was more an open inquiry. I haven't fully tried that one, but how long would it take Bill Gates to give away his fortune? You would just want to set some parameters. Or if you wanted, you could just say he gives away $1,000 a day or $1 an hour, and be surprised. He'd never give it all away, because billions are big. And number 20, how many centicubes would fill the room you're in? Pretty classic. I was once in a gym and I just threw a single one. I was like, that's astonishingly small in this gym. Number 21, again, more open sort of Fermi problem. If you're to substitute million for billion, I think our curriculum goes such like, okay, in grade 6 they deal with millions. And you could ask that then. Big ideas plus playful tasks equals playful mathematics. Just that mathematical objects are meant to be played with. And the more open our questions are, the more they're open to play. And that there's pleasure in thinking about mathematics. So you can think about what that means. And the last one was just play. Okay, so we don't have any work coming in, but I want you to take the ideas and the tasks and consider trying them. Yeah, Matthews is awesome. So, and I'll probably just about sign off shortly, because what I would want is it's past 9, so it's mad PD all day. And so I already took the 8:30 slot when I didn't mean to. I'm going to say thank you very much for being here. Do take the slides, do something interesting with them. Tell me if you do. And if you do happen to be interested in the book when it comes out, you can also let me know, or just tweet me in my natural environment anytime. And I do apologize. It was, yeah, the way I tried to stream it just didn't work. And I definitely learned from that. And we definitely made it work for Peter and Derek and Mad PD. Okay, so thank you very much for coming. I'm going to hit end stream now. Remember, play with your math. Okay, bye-bye.